In 4.7 inverse trig functions, we're going to apply our earlier study of inverse functions back at the beginning of the year to trigonometric functions. So it might be helpful to look at an example that we studied earlier, which was out of a parabola. And when I ask students what they remember about the inverses, one of the first things that they say is that all of the points on the original function swap places. So the x values and the y values are going to swap. So for the inverse function, for example, for the first point, the negative 2 comma 4 would become 4 comma negative 2, and then negative 1 1 would become 1 negative 1. 0 0 would of course stay at the origin. 1 1 would kind of swap and again be identical, and then you get 4 2. And if you connect those dots, you get a very nice sideways parabola. But then that presents a problem. And what's the problem with that? Well, if it's supposed to be a function and we have a sideways parabola, it's not going to pass the vertical line test. And it can't be a function if it doesn't pass the vertical line test, because you can't pick an input and have two different outputs for that input. That's the problem with this graph. So there's a couple of things we have to watch out for. We have to make sure, of course, that the original function passes the vertical line test. And then the inverse function has to also pass the vertical line test. And the way that we can ensure that happens is to make sure the original function passes the horizontal line test. Because if it passes the horizontal line test initially, then it will pass the vertical line test when it is inverted. So what we did back then was, we said, okay, well, we can actually use part of this parabolic function. We just are going to have to restrict the domain. So what we did was we picked either kind of the left or right side and said, okay, well, we'll just take the right side and we'll make our domain from 0 to positive infinity. And if we just take the right side of that graph and we just ignore the left side of that graph, when we invert those points, then we're going to leave these points behind. We're just going to be leaving the points that are in the domain of this side. We'll flip-flop those points. And now we've got, if we ignore that left side, we have a function that passes the horizontal line test, and now the inverted function that passes the vertical line test. So, and in doing so, what you're going to get is a function where if you pick every single input, every x value, you're going to have one unique y value. That's a one-to-one function. So for inverses, characteristics include the x and f of x points are going to swap. We're going to also see the functions are going to pass both the vertical line test and horizontal line tests. The functions are going to be one-to-one, which means they have one unique y value for every x value. And a byproduct of all of that is we're going to see that the function and its inverse are going to reflect about the line y equals x. And so those are the key characteristics. Now let's bring that forward now to inverse functions. So we look at sine x. Sine x is a beautiful sinusoidal function that's going up and down, oscillating forever and ever. And so immediately we say, you know, can y equals sine x have an inverse? If it has to be 1-to-1, and it has to pass the horizontal line test right off the bat, then this is going to fail miserably, because when x, whoops, when it moves through anywhere on the function, it's going to pass at multiple points. So right off the bat, we're going to need to restrict the domain, and we need to make a selection. So if I restrict the domain like this, would it pass the horizontal line test? Sure. If I pick this, sure. If I just pick this piece, that would pass. If I picked a longer piece, that would pass the horizontal line test. So there's a lot of different segments that we could use that would pass the horizontal line test. But what we're going to do is we're going to restrict it based on the accepted restricted values for y equals sine x. And those are a special set of values from negative pi over 2 to pi over 2. I'm just going to highlight this section here. And that's from negative pi over 2 to pi over 2. And so that's going to be our domain restriction. And the rest of the graph we're going to leave behind. So in order for it to be 1-to-1, it must pass the horizontal line test. And to pass the horizontal line test, you need to restrict the domain. And that restriction is going to be from negative pi over 2 to pi over 2. And what that does when we restrict it from negative pi over 2 to pi over 2, which incidentally is in the fourth quadrant, so quadrant 4 and quadrant 1, that gives us gives us an increasing function that's 1-to-1. There's no repeating y values. We get the full range of values from -1 all the way up to 1. So if you think about all your unit circle exact values, the maximum is 1, the minimum is -1, and this would give us all of those values. And it's going to pass the horizontal line test, which means that when we take the inverse, it will then pass the vertical line test. So the definition of an inverse sine function in terms of notation is said two ways. We say y is equal to arc sine. That's a kind of the very historical way of saying the inverse sine function. And the more contemporary way of saying it is y equals inverse sine of x, like this. This is kind of the post 1810, and that's the year 1810 way of saying it. But realize that is not, when you see that as, it looks like an exponent, but that's notation. This is not algebraic. This is not saying inverse sine of x is not the same thing as 1 over sine x. This is not algebraic. So just be careful of that. You have to realize that is just the way the notation is written. So we have a choice of just the way we want to represent it with arc sine or inverse sine of x. And the function inputs, what's interesting about this, when you're doing an inverse, your outputs become inputs, the inputs become outputs. So normally we put an angle in the function, and those angles here is what we put in, and then we get the exact values from -1 to 1. This is going to be in reverse. So these are actually going to be your inputs to the function. And your angles, and there is a little typo there and I change it to y. The angles are your outputs. And as we've said, the domain and the range, they are going to swap when you create the inverse of sine. So if you were to look at, say, down here in example 1, the arc sine of negative 1/2, I want you to think about if negative 1/2 on your unit circle facts, what angles would give you that value negative 1/2? So if you work your way around the circle, sines are negative in the third and the fourth quadrants. They're negative, and they equal negative 1/2 at 7 pi over 6 and also at 11 pi over 6. So this is in quadrant 3 and this is in quadrant 4. Well, here's the thing. So it looks like there might be two angles that would give you that output of negative 1/2. But in order for it to have an inverse, we have a domain restriction. We can only report out values that are between negative pi over 2 and pi over 2. So those are fourth quadrant and first quadrant. So we can't even report out the 7 pi over 6 because that's outside the domain. So we're going to just take that out. But even 11 pi over 6, if you look up here, 11 pi over 6, that is beyond that's almost to 2 pi. So that's, be out here, and we need to be in this range. So 11 pi over 6 is actually in the fourth quadrant here. So we're going to have to rewrite that as a negative angle so that it fits between negative pi over 2 and pi over 2. So we are going to rewrite a negative pi over 6 for our answer. And that is because of the domain. So it must be written between negative pi over 2 and pi over 2. So you might have, my fourth quadrant is legitimate, but you're going to have to write it as a negative angle, which we're not used to doing very often. So I want you to take a minute and think about where these other exact values lie on your unit circle, and then predict what those angles would be that would be actually the outputs of these inverses. Think about what angles would be within the domain restriction here, and pause the video and then continue. Okay, so we're thinking about the input is an exact value. Okay, and the output is going to be an angle. So where on our unit circle do we have a positive root 3 over 2? We have two places where that occurs, and that's going to be in quadrants 1 and 2 for a positive signs, at pi over 3 in quadrant 1, and 2 pi over 3 in quadrant 2. Well, from our domain restriction, we have to have angles in quadrants 1 and 4. So we're not going to be able to use this one, but we can use pi over 3. And that does fall within negative pi over 2 domain restriction. So we're good to go there. For C, you're probably puzzled by that. It's like, wait a minute, that's 2. I don't remember any exact values in our unit circle that give us 2. There's no angles that produce that number. Well, you're right, because 2 is outside. That's larger than the maximum and min values here for sine. Whoops, that's going to be here and here. So when the inputs are going to be between 1 and -1, and 2 is up here. So if you tried to actually put this in your calculator using your inverse sine button, it would give you an error. And so this is undefined. Okay, and the reason for that is that your input is outside the domain, which is -1 to 1. And then for D, we have arc sine of √2/2. Again, that's positive signs are in quadrants 1 or 2. And so you would, if you remember, that would be pi/4 at 45 degrees and 3 pi/4 in quadrant 2. Quadrant 2 is outside of our domain restriction, so it's just going to be pi/4, and that works perfectly fine. So you don't have to show both of these values and cross them off. I'm just kind of repeating out of the thought process kind of out loud on paper. Anyway, the same process works for cosine. And so as you can see, we've got this wonderful infinite sinusoidal function. We're going to have to restrict this down in order for at least a chunk of it to pass the horizontal line test. And the accepted domain for cosine that's used, and this is used in your textbooks, your calculator is programmed for this, any website that you're going to use to like a tutorial on the inverse trig functions, this is the acceptable domain. Everybody is going to be on the same page if we restrict the domain from 0 to pi in this case, which would be quadrant 1 and quadrant 2. That gives us the full range of values from -1 to 1. And it will pass the horizontal line test and the vertical line test. So given that, I've got actually a summary down here of all of them. So for your inputs for sine and cosine, they're going to both be between -1 and 1. But the range, your outputs, your angles are going to be quadrant 4 and quadrant 1 for sine. And then they're going to be quadrant 1 and quadrant 2 values for cosine. For tangent, there's just a little note here about tangent. It just works the same way. I'm going to draw a little sketch here of our tangent function. Standard tangent function goes through 0, and we have asymptotes here at positive pi/2 and negative pi/2. And then what's nice about tangent is that just that initial part of the function that's around at 0, 0, that has the intercept 0, 0, it automatically would meet the horizontal line test and the vertical line test. So the domain restriction is very natural. You're just going to restrict everything down to that very first cycle of tangent. So from -pi/2 to pi/2. And again, that would be quadrants 4 and quadrants 1. And that is also illustrated down here in the chart. What's interesting about the values, of course, because tangent, the outputs on just the regular graph go from -infinity to +infinity. So when this is inverted and all of the x and y values switch, those are going to become, when those points swap, the domain now is going to be between -infinity and +infinity. And then the outputs are going to be restricted between negative 90 and positive 90, quadrants 4 and quadrants 1. And if you take the points of these restricted functions and you flip all of them, you swap them like we mentioned at the beginning, the x's and y's, notice your inputs are those exact values and your outputs are your angles. You're going to get, the graphs are flipped, and cosine is going to go from 0 to pi. Tangent, it's going to go from negative pi over 2 to pi over 2, but notice again, we're going to be moving from negative infinity to positive infinity with the domain of values that can go into that tangent function. So all of this, these swap from the original functions. So to finish off from day one, I want you to take a look at these 5 examples. I want you to think about, all right, what angles would produce root 2 over 2 on your unit circle for cosine, and then figure out what that angle is that's going to meet your domain restriction. So your final answer has to be a cosine from cosine value from quadrants 1 and 2. And remember, we're talking angles here. So pause the video, give them a try, and then check yours with mine. Okay, to find these values, these outputs, which are angles, for arc cosine, we're looking for the angles that would produce root 2 over 2. And I'm just going to use this other little work surface to illustrate. Root 2 over 2 is going to be positive for cosine in the first and the fourth quadrants. Okay, so you have a positive cosine, and so that would occur at pi over 4 and at 7 pi over 4. We can't report out both of these values because we need to remember that cosine is only valid from 0 to pi. So from here to here, the only one of those values that is valid would be pi over 4. So we're not going to use the 7 pi over 4. And you don't need to write both values on your paper. We're just going to be writing pi over 4, and we're all set, all done with that. Inverse cosine of 3, again, we know that the input there is outside of our domain, which is 1 and negative 1. So right off the bat, we know that this is undefined. Next, for inverse tangents of negative 1, so back to our little work surface, we know tangent is negative 1 in the second quadrant. Okay, so your tangents, you've got negative x's and positive y's, and then also in the fourth quadrant, you've got positive x's and negative y's. And those values, the x's and y's, are identical to each other except for the signs in those quadrants. And so that's going to give us the options of either 3 pi over 4 or 7 pi over 4. So so given our restrictions here, which is negative pi over 2 to pi over 2, in here, the only one that fits that bill is 7 pi over 4. We've got to be careful, though, because 7 pi over 4 is not a number that is within this range. It's bigger than pi over 2. It's really like going around like this. So we got to write the 7 pi over 4 as a negative pi over 4. So that's how we're going to report out that value. So at first glance, we would say 7 pi over 4, but we're going to rewrite it as negative pi over 4. And again, you don't need to show the process for that. You just need to give the final result that is within those domain restrictions. Arctan of 0, tangent of 0 degrees or 0 radians has an output of 0. So this is 0, and that is perfectly fine. That fits within our restrictions here, our output restrictions for tangent. Arc cosine, negative root 3 over 2. So we're looking for a value that is in the second and third quadrant. So this is where your cosines are negative. And that's going to be here at 5 pi over 6 and at 7 pi over 6. That's where you're going to have a negative root 3 over 2. But we're going to, if you again look at our domain restrictions here, for cosine it needs to be in the first and second quadrant. So we're just going to report out the 5 pi over 6. And your calculator is programmed for these values. We'll see how that plays out when we start doing a little bit of calculator work. So we're going to stop there, and what you should do is get into MyLab and start working through the basics on these inverse functions. And then on day 2, we'll continue with some calculator work and using these in some more sophisticated combinations and applications.